Testing, 1, 2. Hello. 1 2 1 2 1 2 1 1 1 1 1.
Keep talking.
Oh, come on.
Everybody can hear you on the internet, so say something nice.
Okay, Boland is a cool guy. We all love him. And yeah, we're glad to be here at Ethos Research headquarters. So, is it now Is it now working? Can I stop now?
Just a little bit more.
Okay,
So good.
a little bit more. So good. Yeah, that is kind of embarrassing. So I will stop now. I didn't know that.
give me some 1, 1, 2, 3s, and I'll.
Okay. 1, 2, 3. One, two, three. One, two, three. 1, 2, 3. 1, 2, 3.
I guess when you're ready, but remember you have to stand in front of that thing.
Oh, okay. Is this good? Let me, testing. Are you sure? Testing, 1, 2, 3. Is it okay? Testing.
Come over here a little bit.
Do I have to sit down?
Oh no, A is red. I mean A is.
Should I hold it? Hello?
All right,
Testing.
We might get started now. So, all our cameras are recording and our live streams are streaming. Neil, do you want to test that out?
Testing, 1, 2, 3.
I think we're good to go.
Okay.
Neil, take it away.
Good evening, everyone. My name is Neil Pandya. I would like to welcome you all to the third Cyberspectrum Meetup, which serves as a forum for the exchange of knowledge and ideas related to software-defined radio, and generally aims to get people interested and excited about the applications that can be realized with SDR technology. Engineers, students, hobbyists, enthusiasts, and people of all experience levels are welcome, no matter what your software or hardware background. At each meetup, people from the community will have the opportunity to present their work, projects, and ideas to the group. The event tonight is being sponsored and hosted by Edis Research. Our first speaker will be Julian Arnold, who is the Perpetual Intern of the Month at Edis Research. He will give a short discussion on the detection and synchronization of 802.11a OFDM packets in GNU Radio. Our second speaker will be Derek Cazell, who will give a talk about applying evolutionary algorithms to determine optimal signal constellations for phase shift keying. Our third speaker will be Alex Ray, who will talk about some of the radios, antennas, and protocols that he's currently working on as part of the just-started NASA Cube Quest Challenge, which is a competition to get high data rates to small satellites that are far away from Earth. All meetup presentations will be recorded and posted online, as well as streamed live on YouTube. The previous two events have already been posted in HD video. For people who are off-site but would like to contact the group here in Santa Clara, we have set up an IRC channel #Cyberspectrum on Freenode. Future meetup locations will alternate every month between South Bay, here in Santa Clara, and in San Francisco. We expect to host the next Cyber Meetup in Noisebridge, a nonprofit hackerspace in the Mission District in San Francisco. Please check the Cyberspectrum Meetup website for the final date and location in about a week. As always, a list of speakers and presentations will be posted a week prior to the event. If you have any topics for future talks and presentations, we would like to thank all of our speakers tonight for their efforts and enthusiasm, and we would especially like to thank Edis Research for providing the space and hosting the meetup. Free beer and pizza are available in the front lobby area, so please help yourself at any time during the event. So without further delay, let's get started. Ball and Siebel will make a few additional announcements and introduce our first speaker.
Thank you very much, Neil. Yeah. We have this awkward thing again. Oh, Julian, now I don't have the clicker for my thing. So thank you all very much for coming once again. Can you tell me how it's framed up? I'm just trying to perfect the live stream, you know, because I just sort of do it as a bit of a hobby, and I like to get everything working. And every time we sort of crank up the notch on it a little bit, today we're actually doing HD for the first time, so hopefully those out there in internet land can see us. But thank you very much all for coming, those of you that have physically come this evening, and for those of you joining online, hopefully you can see and hear me all right. Please comment on Freenode in the Cyberspectrum channel, or on Twitter, or on the YouTube feed if you have any feedback regarding the streaming. Now I've just got a couple of very quick intro slides. Again, please join IRC, even if you're in here and you want to chat, or if you want to tell your friends to join. We have this dedicated channel. This is sort of the hashtag that we use on Twitter as well as on IRC, so join there. There are actually quite a few people on there already, and it's a great place to sort of discuss and be part of the virtual audience, if you will. And I monitor it quite closely, and if there's any feedback or what have you, then I might relay it, or if there's a question from the internet, then that's a valid way of doing it too. Neil already mentioned, and I'd like to again thank Edis Research for sponsoring us and hosting us. That's the beer and pizza, so please enjoy. Again, as I mentioned before, we're trying to build this community, and it's been really, really encouraging to see the number of people that have joined the Meetup group, and also that have been attending both the Meetups down here and up in San Francisco. We're looking forward to another one next month up in San Francisco, hopefully at Noisebridge once again. And I would really encourage you, or if you want to spread the word and ask your colleagues and friends to submit a talk if you have an idea, but also if you have something that you'd like someone to discuss, then also just comment on the Meetup page. We've had a couple of people asking about Linrad and multi-PSK. We have a guy that next month will be joining us remotely to do a presentation on multi-PSK. He's really excited about it and is going to put together a nice little demo of that. So I'm quite excited about that. And so we encourage all sorts of talks, and also at any sort of level as well, we'd like to sort of cater to everybody. Once again, if you look at the pages page on the Meetup site, this is where I put the Meetup links for each of the Meetups. There should be 3 there already. The first 2 will have links to the slides and media and other sort of interesting tidbits there, so you can refer to that after the fact. And as I mentioned, keep an eye out on the Meetup page, Cyberspectrum. If you want to follow on Twitter, then I tweet about updates there, and hopefully we'll be back at Noisebridge. Could I just inquire, how many of you actually made it up to Noisebridge? A couple of you. Oh, that's great. So we'll try and do that again. And I just wanted to point out that for those of you that either watched on the internet or were here for the very first Meetup when Kevin, where are you, Kevin? There he is. When he did that absolutely incredible talk on an introduction to DSP, he has actually put that up online for public consumption now, very recently, and all the rage on Twitter. So if you want to have a look at this URL, you can actually experience his slides, so to speak, live interactive web browser using the very latest web-based technologies. It's really cool, so check that out.
Yeah, my wizard reader doesn't work in Firefox for some reason. I just showed this not how to work on that.
I think everyone's capable of installing Chrome, so they should be good. And if there was any reason to install a compatible browser to experience something cool. So, getting out of the business end of this evening, I'd like to do a bit of an introduction for tonight's speakers, visually, if I may. At Broadcrap, Julian Arnold, we love him dearly, and he's very proud of the award that we bestowed upon him last month. So, congratulations again, Julian. We have, over here, Alex, who's going to be doing a cool talk about space probes and Batman modulations. Or Batquam, really. Looking forward to that. And of course, these are the Twitter handles if you want to follow these fine folk on Twitter. It's also on the Meetup page if you want to follow them there. And Derek is going to talk about some more. So really cool. Oh, it's all the way down the back there. You ready? Did you finish the slides?
I did.
That's great news. Then we got the whiteboard here for you as well. So yeah, some really radio research, but also combined with evolutionary algorithms. So bringing in a slightly different discipline. Welcome, please come in. Bringing a slightly discipline to add a bit of extra spice, if you will. All right, so that's me. Julian, do you want to do your thing? For those of you that are wondering, that's a bit of a reminder for me to do something. So I shall give you the audio as well. Seems like I'm bestowing some sort of great honor on you.
Yes, our attention.
Yes. So we have good evening from Los Angeles, and we have good evening from Burbank as well.
And we have no video.
Yeah, I found the resolution needs to be changed. Oh, I was going to fill, but it looks like we're okay. Julian, what kind of background are we looking at there?
I don't know.
What's your background?
It's included in my distribution. So. Yeah, so welcome everybody. So most of you, I guess, know me already. I'm Julian, I'm interning with Ethos Research. And as always, I was not forced to do this small presentation. So this time, I'm going to talk about detection and of 802.11a OFDM signals. So first, I would like to ask who of you knows about OFDM in general and the theory behind it? Okay, quite a few. Okay, that's good. So OFDM, very, very basic. So it's a special kind of multi-carrier modulation. All the carriers are orthogonal to each other, and which allows us to pack the carriers very dense. So if we take a look at, well, let me explain a little bit more. So what does it mean, multi-carrier? So we take our data, and normally we would modulate it on a carrier and then send it over the air. So what we do in multi-carrier, we try to take our data and modulate it on multiple carriers, so that that we do not occupy as much frequency per carrier, so that our symbol time can be longer, which makes multi-carrier modulation schemes very good for multipass channels. So as you see here, this graph depicts like an OFDM modulation where we have 4 channels, and each of these channels will carry like your normal, what you know as a normal signal. So there can be a Batman modulation scheme on it, or whatever you want. So each of these channels can carry a data stream, and in the time domain, every symbol is pretty long compared to if you would use the whole spectrum just for one symbol. So that's pretty handy. And what's also pretty handy is that you can adjust to your channel pretty easily. So if your channel has, I don't know, severe fading, you can just adjust to your channel by picking the right carriers that are not affected by the fading. So that's a pretty handy technique, and it can be shown that this technique can be very easily utilized by using the FFT and the IFFT for modulation and demodulation, which is very handy. And so I was like, well, that sounds great. I have a software-defined radio laying on my desk, and why not give it a try and see if I can just take the data, put it in an FFT block, and have my Wi-Fi signal coming out. Well, it turns out it's not that easy. So we take a closer look. So block diagram looks like in general. So we take a look at the receive side, which is here. So you have your data coming in, you're sampling it. Then yeah, you remove a cyclic prefix, but we don't talk about that now. It's not that important for synchronization. And then here you have your FFT block. So you pipe your data in your FFT block, make a serial to parallel conversion, and then you make a parallel to serial conversion after FFT block, and out comes your signal. So that is great. That is very easy. But there are a few problems to that we have to account for. So till here, questions? Oh, good. So what are these problems? So because these carriers are very densely packed, we have a problem with carrier offset. So as I said, it's good for multipass channels, but there's no free lunch, and so we have to deal with frequency offset. And we need to synchronize to our signal very, very good in frequency, and also we have to do like a frame detection, a time synchronization. So these are the two kinds of synchronization we need to do: frame synchronization and frequency synchronization. So, and if you try to get some more information about that, you will stumble upon this very popular algorithm by Schmiddle and Cox, which is, I guess, the most popular algorithm in that field. And yeah, I'm going to explain how this algorithm kind of works.
Can I ask a question?
Sure.
You said frequency synchronization. The delta between the channels pretty fixed, and so the frequency synchronization I'm talking about is for the whole array of signals?
Right, so your whole spectrum will be shifted. And this is a problem because the carriers are very, very close together. So if you shift by a little bit, like more than half let's say more than half spacing between the carriers, you have a very severe problem.
But the spacing of the different carriers, you don't have to synchronize each carrier separately.
No, you do it at once. So you calculate one frequency offset, and then you should be good, hopefully. Yeah, one more? So in this Schmiddle and Cox algorithm, there are two stages. So there's a stage.
No, I'm just talking about just
Yeah, right. So they.
megahertz, 10 megahertz, 100 megahertz.
Really, just for the benefit of Ellington, can you repeat the questions? Like, to explain how we hear.
Oh yeah. So the question is, what is a typical value for this frequency offset? And so what I've seen on my desk, so doing my case studies, it was definitely below like 50 kilohertz. So wasn't that bad. So the algorithm could easily cope with that. But you need the algorithm. You need the synchronization.
Actually, I can answer that exactly.
Okay.
There's the IEEE standard actually defines
Oh, that's good.
what's allowed. And for 811A, it's 20 parts per minute. It's the what when you transmit, that's how much you're allowed to do.
Okay, so 20 parts per.
So you can multiply 20 parts per million times your carrier frequency.
Right.
And that'll give you your answer.
Okay.
So if your carrier frequency is just, 5 gigahertz, then it's 5 times 10 to the 9 times 20 times 10.
Right.
And I'm on my second beater, so.
Same for me.
Where's 100 kilohertz?
Yeah, that's what I observed. So yeah, but you definitely need to do your synchronization. So what does this algorithm do? So first, it introduces a preamble in your signal. So you spend some extra data, let's say, to do this synchronization. You don't get it for free. There are approaches to do it without extra data, but this one uses extra data. So you put a preamble in front of your symbol, and with this, you are able to track the time and the frequency offset, which is pretty handy. So and what they do is they use an OFDM symbol, which is only utilizing the even frequencies, which results in a symmetric symbol in time domain. So in your time domain, the signal looks like 2 times the same thing, which is pretty useful because what the algorithm then does, it takes this data stream, the cross correlation, and the formula here. So, but that's not very interesting. So let me maybe depict it, what's happening there. So let's say we have a constellation plot, and our first symbol is looking like that. All right. Then in this case for 802.11, you can say that the second half begins after 16 samples. So you go 16 samples further in your data stream. And now you know, because these symbols they are 2 exact same halves, you know that after 16 samples, you should see exact the same symbol, right? Is that clear? Okay, good. So, but now what you get is, let's say, something like that. So your constellation has rotated. So you have a phase shift in your constellation, and this is due to your frequency offset. So now the algorithm goes and takes the complex conjugate and multiplies it with the shifted version. So complex conjugate this, multiply it with this, gives you the difference in phase. So you will get exactly this phase offset. And this is pretty handy because then you get first the correlation peak, which gives you the time offset, and you can get this phase difference, which gives you your frequency offset. So this is a pretty clever and pretty handy algorithm. Is that kind of clear how that works? Yeah, I assume it is. Okay. So I'm just going to demo it because I guess that's more interesting. So what I did is, because we all love GNU Radio, right? So I wrote a small GNU Radio blog that's doing exactly what I depicted here. So here are your samples coming in. This is the method where you process all your samples and you iterate over all your incoming samples. And here you have your correlation. So you take the sample, conjugate bigger, yeah. Is that good? Is that good?
One more.
No. Yeah, so complex multiply with the 16 samples shifted version, and then you're adding them all together, and hopefully you get a good output. So this is exactly what we're doing here, just for every sample in this preamble. So you add them up, you kind of stack them together. Yeah, so it's very, very, very simple actually, and let's take a look what it's doing. So this code is in this block here, and if I now run it, so all these O's you see down there is just because the block is so efficient. So no. so it's kind of working. So what do we see? So now this is the algorithm running. And so this blue line gives you the magnitude of the correlation. So you can see every time we receive a package, this correlation is forming this plateau. And with this plateau, we can do our time synchronization. So we know when there's this plateau, there's the beginning of our frame. And what the green curve is showing is the phase of every sample in that plateau. So yeah, most of the time you see when we are on this plateau, our phase is kind of constant. So this is corresponding to our frequency offset, which should be constant during this interval. This is exactly what we want to have. And you see everywhere else, it's pretty random. And furthermore, you see that we are pretty close to 0. So that's, yeah, that's pretty good. And if I now change my carrier frequency, what would we expect? We would expect this phase offset to change. So yeah, I don't know if you can see it. Now I changed the carrier frequency, and our phase offset is now somewhere here, where before it was down here. So this algorithm is working. It's tracking the phase. It's giving us the time offset. And so that's the first step you need to do when you want to decode OFDM signals. Yeah, and that's it. No, good. Thanks.
Are you finding the phase in the time domain or the frequency domain?
That is all in the time domain. Right, yeah. So what, if you take a look at the block diagram. So this is my block, which is just doing the correlation, right? And what comes out of this block, it's just split up in magnitude and phase.
Okay.
And then plotted on this time scope. Yeah.
You don't actually need to split it, by the way.
Sorry?
If you just put the complex into the scope, you'll get 2 lines.
Oh, is it doing that for me? Oh, I didn't know that. Okay, so we don't need these. But it's good for demonstration purposes.
Wait, actually, no, sorry, magnitude argument. Sorry, I was saying it'll give you I and Q. That's not what you want. Sorry,
No.
I was wrong.
Okay, good.
So yes,
So-
this is used. That is used.
Glad to hear that. I did. What? Explain the green line again. Okay. So, yeah, there was a question.
Channel 1 and channel 2.
So the green line is giving us the the phase of our 2 correlation samples. So exactly this difference between this sample and this sample, 16 samples away from that, from which we can derive our frequency offset. So this is what the green line is showing. And the blue line is just giving us the magnitude of the correlation. Okay.
One thing I would expect is a constant phase ramp.
No. Why would you expect a phase ramp?
Because if you have a constant frequency offset, it means you...
No, that's not how the...
thinking that this-
Yeah, that's not what the algorithm is, how the algorithm is working. The algorithm is always giving you the same difference. So because this sample and this sample, you get this offset. You go one sample further here, and you go one sample further here. The difference between the 2 samples will be the same. It will be your frequency, so related to your frequency offset. It's not going to change.
Yeah, okay, I thought you were posting the samples that were not correlated for the phase, but that you're posting that correlated.
Right, so this is, so it should be, if it would be working perfect and there was no channel impairments, it would be a perfect line, in theory.
Is the same synchronization algorithm also used in other protocols?
What do you mean?
I mean, this way of detecting the preamble of your frames is that also used for?
Oh yeah, it is, like in other 802.11 cases. Oh, yeah, the question. If this kind of synchronization is only used in other protocols, and the answer is yes, it's used in a huge variety of protocols, because most of the time you have to do synchronization, and most of the time you're going to use a preamble, and most of the time you're going to do like a correlation approach to get your time and frequency offset. So yeah, it is.
But it applies to OFDM.
It applies to OFDM, yeah.
Does it apply to something other than OFDM?
Right, because this is pretty general. This is not really OFDM related because we created the preamble so that it looks kind of nice in the time domain. And so it's not really OFDM related in that sense. So you can use it for other protocols as well. Maybe not exactly, the preamble would change and stuff like that, but the theory will be the same. Thank you very much.
So while we do a bit of a sticky tensor from Derek's going to set up, there's still, I think, more. Is there more pizza outside? Feel free to grab another slice if you feel like hungry. I know I'm going to. I'm also going to get a drink. This is not working. Oh yes, if you want to get on the
Thanks.
Sorry, I
I wasn't good enough.
Wi-Fi network to connect to is called.
Can you take it off?
And the password I will write.
What was it? Yeah, okay. When you get a moment when you're speaking, just put this on. Did you have any help with anything, or can I give you a break or something?
No. Okay. Once I get plugged in now. And projecting, I mean, very around the restaurant. There is magic. Oh, man. There are times that I do enjoy Windows. Oh, come on. Yeah. Cool. The next best thing to a wireless controller.
Not mine, sadly, but I love this project. This is my favorite way of explaining what evolutionary algorithms are. Because here's a computer that is completely dumb. Oh, come on. Oh, it's trying so hard. I have to say, usually it does much better than this. Yes. Yeah. I should get rid of this. Yeah. This is the much faster version. It starts, how many cars? Starts like 20 cars simultaneously. I'm breaking a Porsche NDA here, you know. This is what the next year's model is going to look like. Yeah. So Valiant, just let me know when I should start. This is the pre-show. No rush. Oh. Is there anybody else missing? I thought someone gone outside. Everyone's back? Derek, if you want to take it away, then, and you got the audio on?
Yep.
I think that's all.
I think I'm good to go.
All right. Take it away.
I will. So, hello. My name's Derek. I'll start the actual slideshow in just a moment, but I love leading with this just because this is pretty much what got me interested in evolutionary algorithms. This computer knows absolutely nothing about cars. All it knows is how to join a whole bunch of points together, rotate a wheel, a basic model of physics, and that things that go far are good. And it has no other judgments. And you can basically just sit here and it will continue evolving more and more cars. And you end up with something that usually looks like a motorcycle, but some of them start having these really fun features, like the one that has a spike out the back that's preventing it from flipping over backwards and then ending up on its back easily. And so you can actually see it evolve these very interesting attributes quite quickly. And given a few generations, especially with this one where it starts everything at the same time, you can see these traits being inherited and passed around and it trying out different areas of the fitness space. So, unfortunately, let's call that for the day. And this thing is still rolling along on car 19, so.
Ever evolved to something with
No, sadly. But you can set it up to have, only one wheel at maximum, and it'll start with a whole bunch that don't have any wheel. That's just painful to watch. What's also fun is giving it the option of having 20 wheels, and watching it try to figure out what on earth to do with that. Because usually it ends up with these very large structures that end up tumbling backwards on the first hill, because it just can't get enough torque and its center of gravity is too high. And eventually it will decide, 20 wheels, bad idea, and start evolving down a path with 3 or 4 wheels or something like that. So yes, get my wireless control here. So yes, I'll be talking about the using algorithms with regards, in the end, to digital modulation schemes. And this was a project that I did for a course during my master's, and found it to be a lot of fun. And then when the topic, they were short a speaker for this evening, this was something I was very excited to do. So who am I? My name's Derek, as I've said. I got a master's just up the road at Carnegie Mellon, Silicon Valley. I graduated in May, and I'm moving to the UK soon, so that's good fun. I worked at SpaceX on wireless sensors for the first stage of their rocket, so I can happily say I haven't blown up a rocket. I worked for Range Networks on software-defined cellular base stations, and I've been an amateur radio operator for a number of years now, and I'm the youth coordinator for the Santa Clara Valley region. And I've done research, which I'm going to talk about today. So the outline. What is evolutionary computing? What are the steps involved in making these algorithms, and how do they run? With a little bit of a diversion to what are signals, because I promised that on the Meetup page, and so it's in there. And then what happens to them? What happens to signals in a computer? I think I actually tore that bit out. And then the last bit will actually be talking about how I take all this talk of what goes into an evolutionary algorithm and build 3 different algorithms to optimize analog and phase shift keying constellations. So what is evolutionary computing? And this is the broad field. It's a subgenre of artificial intelligence. So we're trying to take a computer and make it do something that's not completely dumb, and do it without having us have all the smarts, which is part of the reason why I love evolutionary algorithms. You can take a really, really complicated problem, know just enough to be dangerous, teach a computer that, and let it go do all the hard work to actually find a good answer. It's an optimization strategy is the way I look at it. There are some other applications where you can model systems and figure out unknown parameters of systems and stuff like that. And it's stochastic. You aren't guaranteed an optimal result. In fact, it's really quite likely that if you're doing it right, you won't get an optimal result. You'll just get, hopefully, a quite good answer. It's good for large, complex search spaces, because we're not going to explore every possible option here. So these are for spaces where that just takes too long. We want to find a good answer. We want to find it, before 10 years from now. So these are kind of the broad categories of problems that we can look at here. We're going to look at optimization tonight. And this is where we really don't know what input to provide this system in order to get the best type of output. But we have an idea of what makes a good output. We can say low bit rate, or bit error rate for a communications channel. The next one down is system identification. We have a whole bunch of inputs that we know, and we have a whole bunch of outputs that we know, and we have a model for what goes in the middle, but maybe we don't know what degree of multipath we're getting here, or what's the time delay through this system, or how much noise is there in this black box. And so given that model, we can have the evolutionary algorithm search through the parameters, and it has just enough intelligence to know it's getting closer to the actual system or something that is equally representative of it. And then the final one is simulation, which you have a known input, you have a known system, and you pretty much just run the values through. And I haven't done any work with that, so I don't actually know why you would use an evolutionary algorithm for that, but you can. This is the basic flow of it, and it's, as you can see, it's a cyclical process. You initialize it with an initial population, which is just a whole bunch of candidate solutions. And you can choose these completely randomly. And that's actually usually the best approach. That sets up a population. They set each of these candidates to become parents for the next generation. These parents then undergo mutation and recombination to create a whole bunch of new candidate solutions, which are just a little bit different than their parents. So you're now exploring related solutions in this problem space. These offsprings are then evaluated, and we can say, is this a good solution? Is it a terrible solution? Is it just a little bit better than the last one that we've seen? Select a bunch of these to go on to the next generation, and then repeat the process until either we get really tired because it's taken an hour, and our termination condition is run for 1 hour, or it could be, we've gotten a good enough answer and we know what good enough is. And so in pseudocode, this is pretty much exactly what that last slide was. We initialize a population, evaluate each candidate, and then start iterating through this process of generating some new solutions and trying them out. So these are the main components of it. You have to pick how to represent your problem, and I'll go through each one of these in the next few slides so you get kind of a better idea of how you would actually set up a real problem with this. So you pick a way to represent each of the individuals in your candidate space. Then you pick a fitness function. How good is any particular candidate? And in the example that I'll go through at the end, my research, we were using GNU radio to actually simulate a transmission and a channel with multipath and noise. And we were measuring bit error rate, and the fitness was proportional to the bit error rate. Population, what is the population? What are the characteristics about it that we end up caring about? A terrible population would be everybody's the same, because there's no genetic diversity there. Oh, and I guess the thing that I missed here is obviously evolutionary algorithms. This is a domain where the algorithm has been inspired by Darwinian evolution. So it's the survival of the fittest. Parent selection mechanism, not guaranteed to have offsprings. True in biology, true in this case. Variation operators, we do want to introduce variety into the genetics, into the population at every generation. But obviously we don't want to have the same amount of mutation at the beginning as the end. Because when you're getting closer and closer to a problem, there's no reason to still be searching quite broadly. But at the beginning, we want to explore as much of the problem space as possible, as efficiently as possible. And then the survivor selection mechanism. So representation. We're working with a computer here. So each individual is going to have a type. And this will be basically a string of values. And one of the classic examples here is the 8 queens problem. You have a chessboard and you want to put 8 queens down on the board without it being an illegal move for any of them, without any of them being able to capture another piece. And there is a solution for this, and actually there's several solutions for this. And so the genotype could be a whole bunch of integers. The phenotype is actually what these string of numbers means. And in this case, you'd have two integers for each chess piece. So you'd have 16 integers, a row for each queen. And so the phenotype is the expression of the genotype. Fitness functions, yes. Defining how good a solution is. This is a picture of a 2D fitness landscape, as they're called. And in this case, let's assume that the higher up a point is, the better it is in fitness. And obviously, if you have the entire fitness landscape mapped out like this, it's really trivial. Who can point out the best solution here? It's that one. But in most cases, we don't actually know what the fitness space looks like. If you took QAM 250, and so you have all these points, anywhere within a unit circle, where should they go to be optimal? We don't actually know that equation. We can make some general statements about it, but actually mathematically solving that is extremely difficult and requires a lot of domain knowledge and computation. And it can be a very simple formula. You could be optimizing 2 integers that are 32-bit numbers and saying, I want them to have the highest value possible. Guess what? Add the two together, and your fitness function is just the higher the better. Population. That image isn't on this slide. Pretend it's not there. So you have a pool of individuals, and this can be 100 individuals, it could be 10,000 individuals, but it's your base population, and it's a whole range of genotypes, and so there's a range of different solutions represented. And you can have them all in just one pool, or you can actually look at Darwin and say, okay, we could divide them up into different genes, and you can see evolution go in slightly different paths on each island. And then occasionally mix results from one island to the other, and that way you actually end up increasing diversity over time. And so when you divide them up, you're generally dealing with what's called diversity maintenance. Over time in evolution, you're going to converge onto similar solutions, especially with a lot of these naive algorithms that I'll explain tonight because it's difficult to get into all the intricacies. And so they'll all converge. The really, really fit individuals will kill off everybody else because they'll outcompete everybody. And yeah, dividing them up on different islands is a good way of preserving it. Or you can say, we're going to separate them out. So all of the young individuals, the ones that haven't survived multiple generations, they're going to compete against each other. The ones that have survived 5 generations are going to compete against each other. The ones that have survived more than 10 are going to compete against each other. And so, these are all just methods of dividing up the individuals to preserve some of the diversity. And our first domain-specific term, there are mu individuals in the population. Parent selection. Parenthood isn't guaranteed. Selection can be, random. It can be fitness-based. It can be deterministic. And there's a whole bunch of different approaches to why would you choose a certain individual over another one? Almost always you're dealing with probabilities in this because you do want to, have a chance that solution that has really low fitness at the moment might actually be exploring a peak. Will this work? No. No, that won't work. So if we do look at this landscape, you can see that there's a lot of local optimums here. And so you could end up with the majority of your population clustered on one of these local optimums and another one right down here. And you actually want a chance to preserve this individual because that one's the one that's actually climbing the global maximum. So in a few generations, it might have the highest fitness and be driving the population along with it. So you do want a chance to explore all these alternatives. Selection. And the next term is lambda offsprings are generated. There are lambda children for each generation. And so the parent selection mechanism, did I talk about it? Not really. Yeah, usually you have a uniform chance of choosing any individual, or you can break it down and say, we want to, that actually is what this next slide is, fitness proportional selection. We want to choose individuals that have better fitness more of the time, because that's basic Darwinism. We want to breed strong children so that the next generation of the algorithm is looking at good solutions. And so this equation is quite simple. It's just the probability that individual I is chosen is the ratio of that individual's fitness over the total fitness of the entire population. But what this does mean is that individuals with high fitness very, very quickly dominate. So you need one of these other fitness genetic diversity mechanisms to preserve some of the other options. Ranking selection is a way of helping alleviate that. We're still going to prefer individuals with better fitness, but only by a little bit. The parameter S here is basically the expected number of children which are children which are genetically children of the most fit parent. So in this case, individual B is the most fit, and if you just normalize the fitnesses, it has a fitness of 0.5. If S equals 2, we want to have, and you're producing 3 individuals, sorry, because there's just the population of 3. we're going to have 2/3 of the children be related to B, and 1/3 related to C, related to A, because obviously we have to round to the nearest integer. And that gets much more interesting when you have large populations. But it just provides a way of controlling and slowing down the convergence a little bit. And there's a whole stack of different methods there that I don't talk about. I'll definitely post a link to this. This was the textbook from the course. It is like $40, but everyone here, I bet, has had a really bad textbook that they've read at some point in their life. This isn't one of them. This is actually kind of like Evolutionary Algorithms for Dummies, but an actually useful one. It leads you straight through everything, and I made it about halfway through for this project, and it served me quite well. And as I said, I'll post the link. It's called Introduction to Evolutionary Computing. Variation operators. So now we've chosen parents. What are we going to do with them? We're not actually just going to clone them because that doesn't get us anywhere. We're not searching any new points. So we use these different operators to introduce some diversity. We obviously want the children to be related. So we're only going to change a little bit of each individual. And these operators are divided up by arity. Just how many parents does it take to make one child? Or how many parents does it take, regardless of how many children it makes. And mutation is the general term if it's arity 1, and recombination pretty much covers everything else. There's some advanced operators, but nobody really uses them.
Question.
Yes?
The amount of variation mutation, is that the descent to have more fit to have less mutation and less fit to have more? The ones that are fit are already almost there, so you don't want them to diverge too much. And then the ones that are less fit, you probably want to go around. Is that something that's done?
It is. So the question here was, if you have individuals that are very fit, intuitively it kind of makes sense that they're probably getting quite close to a solution. You don't want to, do you not mutate them as much as ones with low fitness that probably need to explore a bunch more? So this is basically varying the mutation on a per individual basis, with the criteria being based on proportional to fitness. And yes, that's done. Also, one of the other things that's probably the simpler solution that's more often done and that you'll see later in the code is having it be proportional to the number of generations. So even if you have a really fit individual early on, still mutating it quite a bit under the assumption that it probably won't drift that far, especially if you have 500 points, or 500 individuals in the generation, you'll probably still have exploring that peak. And then having the mutation rate fall off over time so that you're exploring finer and finer points at the end. Done. What also ends up being quite fun is we're talking about an optimization problem here, and I'm already introducing parameters, the mutation rate, PM. Well, how do you choose a good PM? There's some rules of thumb, but wouldn't it make sense to run some tests and optimize that value? We're already optimizing some. You can actually run a self-adaptive evolutionary algorithm where you have all of the individual's genotype, but the entire chromosome of a particular individual will actually include at the end, a PM and a PC for the crossover rate. And you'll end up evolving those parameters either on a per individual basis or on a per population basis over time. And so you have a kind of self-tuning algorithm. So that gets to be good fun, and in the end, you end up with a lot of people writing papers that say, well, we got this result. We then went into the field and we proved it works. But then we talked to a whole bunch of experts, and we have no idea why it works or how you got to this result. But hey, we're not complaining. One of the great examples is there's a whole bunch of antennas that have been evolved, and it's by a professor at Carnegie Mellon who taught this class, which is why I know it. And they end up looking like Christmas trees. And it's completely evolved, and they just had an algorithm that would draw a line, and then with a certain probability create some branches, or branch off in a different, in a different direction at each joint and go for some randomly generated distance, and they'd run it through an EM solver and see what the field looked like. And yeah, these things look like Christmas trees, and everybody stares at it and goes, that can't possibly be a directional, 3 gigahertz antenna. You put it in a chamber, you run it, and they're on satellites now because they work. And you can prove that they work, and so knowing why they work turns out to be not important enough for NASA not to use them. Yeah. And one of the great things here is if you can run an EM solver, you build good antennas because you don't actually have to have that intuitive knowledge of, well, if I elongate this element, it'll improve the characteristic in this way. If you can just define the problem, the algorithm will solve it for you. And there are limitations, obviously, but as an engineer, if you don't have that domain knowledge and you want to be a little bit lazy, it's a nice way of getting a good answer. Yes?
So it seems like that really requires having a good model of physical reality that it's representing.
Yes.
Particular examples of things that work, that we have very good models for, that makes this work, things that we don't have good models for, that don't work.
So the question is, you have to have a good model for this to work, because obviously your results are only going to be as good as your simulation. And so are there particular examples where we do have good models? And anything involving physics that probably anybody in the room would, I don't like making that generalization entirely around here, but I doubt anyone in this room is running into theoretical physics boundaries around a lot of problems. So there's a lot of examples of like fluid dynamics, designing a better propeller and stuff like that, and they've run this. We have antenna simulation down pretty well, and so that does work quite well. The results do reflect it quite nicely. I will fully admit that we've actually never run this on hardware. So we have no idea how well our particular GNU radio simulation matches up with reality. But we hope it's good enough that our results aren't totally invalid. Yes?
So now I read a bit about simulating antennas, at least from the amateur radio perspective, and the state of the art is AEC, which is not the state of the art. But they're also quite full of caveats, like you have to design your model like this, and if you do, and you have these things this close together, then it won't actually give you good results. And so, do you have things that you will take an arbitrary input and give you the right answer, or are you violating the assumptions of the modeling software?
Well, so on a slight tangent, I'll show you a photo later of what it looks like when this algorithm starts cheating. We absolutely will try and find any of those corner cases in your model or in your definition of the problem. HFSS does work quite well as an antenna simulator. Whipple-D is another one that works pretty well, and I found those to be not hard to set up the feed point and then design things based off of that. The professor who taught now has a side company that he's started up, which just sells the Evolution software as a product. So a solution does exist, although I don't particularly know it. But I think HFSS and Whipple-D do work quite well, and Whipple-D does have a freeware version, I believe. It's limited to a certain number of polygons, so you can't do particularly intricate ones, but I do think that one does have a free trial version. Yes?
Randomly bit flipping bit strings for actual real life values like amplitude. Would you want to bit flip the most significant bits less than other ones? Otherwise, it's just going to be the actual data that we have can determine the PM is whether that PM.
So the question is, bit flipping, I mean, if this is it is 8 bits. If this is an 8-bit integer, unsigned, let's assume, or heck, signed, even better, it doesn't seem to make as much intuitive sense to flip this, the signed bit and the least significant bit with the same probability. Yes, PM can obviously be a function which takes into account the indice, the bit significance. And so PM can be a function, it can be a straight value. Yes. And this is where it starts getting into the if you know your representation, you start defining all the parameters with a little bit of common sense built into it, and just trial and error. What you'll start finding, though, is if the ones that flip the most significant bit will tend to have very, very poor fitness if you don't have a very flat fitness space. And so they'll die off extremely quickly. And that's why you have a large population size, so you can accommodate this. And there's some diversity maintenance techniques that allow you to preserve the top 20% of your population. So you're never going, of the original parent population. So the really good candidates won't ever die off. Obviously, that can also be a problem where you stop exploring spaces. But there are balances between these, and you find those out partially through experimentation and partly through reading of what other people have done. And yeah, so for bit strings, obviously, it actually that is actually a category than numbers, like integer numbers or floating point numbers. With these, you tend to be adding or subtracting a random value, say a Gaussian distribution, and the mean of that is usually 0, not always. And the that can be a parameter that you set, or it can be something that gets evolved over time, or something that's a great place for putting in a decreasing parameter so that over the number of generations, the mutation rate will fall off in that way. Bit strings, this could be, if you had 64 bits, this could be representative of, pieces on a checkerboard or something like that. Don't know quite what you're solving there, but that's an instance where you do have a binary thing. Is there a piece here or not? Scheduling algorithms, whether or not something is scheduled for a certain time slot or a certain machine, are instances where bit flipping makes more sense. So mutation continued. There's swapping, so you can swap things in two indices. And these could be, rather than a bit array, imagine this simply as an array of numbers, and you're switching two of the parameters within this array, and it could be the order in which operations are done on 8 machines or something like that. So where swapping does make sense related to your problem. There's scrambling, there's inversion, and these are all just kind of different techniques, which the Wikipedia page covers them, and this textbook covers them well, and there's good results out there if you decide to start implementing any of these algorithms.
The swapping, is it sort of at a, if I think back to biology, is it like at a feature level, like left-right-handedness is one thing we swap with eye color, or are we just talking about the expression of, I don't know, is that kind of what we're talking about with the scrambling and the inversion? I guess a little bit of phenotype or whatever, where the expression of that gene is swapped with something else.
So the question is kind of at what level is this swapping implemented? Do you end up swapping right-handedness with blue eye color, where obviously that doesn't seem to make so much sense. But
I guess what I'm saying is like
or is it at the genotype level?
Yeah, if I've got blue eyes and right-handed, and I want to swap in brown eyes and right-handed, is that what you mean by swapping at features, sort of the feature level of the expression?
Yeah. So we'll see at the next bit where it's crossover, and so you're taking properties of two parent individuals and swapping them between them to make children. But yes, you could obviously have the mutation be, so they call, in genetics, when you have a gene, there are a whole bunch of different alleles, which are the possible values, the possible physical representations that fit into that gene slot. Those are the different alleles. And so you could have your mutation aware of all the possible alleles for a certain gene location and say, randomly choose one of these 10 possible alleles, or and then later on randomly choose to go to the nearest neighbor direction or another. And so you definitely do want to build in that type of context awareness if you're dealing with a problem that has that. We're going to get to where our solution actually, our problem was extremely simple, because APSK constellations are just a string of numbers, and they really are totally interchangeable. And so there's very little intelligence built into our algorithm. We didn't have to deal with that sort of a problem. But people did things like tuning the parameters of stock estimation in the class. And they did quite well, actually. Well enough that I think they put $1,000 each into it and ran it for this last year. I'd love to follow up and see how they've done. Because they were doing well enough that they didn't think that they would lose their money, and they thought that they would beat just random chance. Yes, mutation. Recombination. We can have more than one parent. And you can get cases where you have two individuals and one of them has a very desirable trait and another one has another very desirable trait, and you'd love to get a child that has both of them. And so this is where we can get things where some genes are related to each other. I'm thinking about running at the moment, so think about the ratio of the thigh to the lower leg or something like that. To be a good runner, you really an optimal runner, I should say. You need a good ratio of those two. If you have one too short, one too long, doesn't work out so well. So these genes will co-evolve together in the best individuals, and you really want to move those together. And there's a whole discussion of how you do these crossovers, whether they'll break up these co-evolved genes and whether they have biases. Again, a little too long for tonight. So here you see the 1-point crossover. You just generate a random integer value, and you cut at that point, you swap the two ends. And so you get this result. You can have a uniform one where you go through each indice, generate a random number, and if it's above a certain threshold defined by PC, then you swap that particular indice with the other parent. There's n-point crossover where you slice it n locations and swap between the two, or between the multiple points. And so there's a lot of expressions of this. And again, you can get domain specific. We're dealing with bits here just because they're extremely easy to draw. But you can have it be, very complicated arrangements of an entire model of a leg or something like that being swapped with another individual. Survivor selection. So we've had a whole bunch of children. Yay! But a standpoint of evolution, we do want to throw out some of these individuals. Like I said, there's some value at having a chance for that lowest fitness individual to stay around. He might be onto something. That'd be really good if they were onto something. And so oftentimes it's simply, we have lambda children and mu parents, and we're going to randomly pick lambda number of the parents, and we're going to throw them out. And that's a very simple way of doing it. Some of the algorithms actually will generate the same as the parents, and they'll completely wipe out the parent generation. And that's where it's sometimes really nice to keep around the really good fitness individuals, and so they call that elitism. And so we'll say we have 100 parents, we generate 20 children, we're going to throw out 19 of the total combined pool of both of them, and we're going to bias it so that the ones with the lowest fitness have the highest chance of being thrown out. So you can really, as tricky, as advanced as you like. Usually this is done by assigning some. I did not talk about that. So yeah, you assign some probability to each individual to get thrown out, either age-based, fitness-based, uniform, and then you just spin a roulette wheel, simulated, and randomly pick values and throw out the ones. Yeah. Yes?
Are you trying to keep the population that goes through the system relatively constant?
In general, yes. Mostly from a simulation standpoint, I think. You don't want to be simulating people that you've already simulated, especially if your simulation is deterministic. But also it just doesn't, you're not moving forward if you keep too many individuals around. So you do want to call out some of the poor performers at each round.
But you're keeping parents around.
Usually, yeah.
They'll spin around a certain number of times maybe.
Yeah, and because it's almost never done deterministically, where you get rid of the n lowest fitness people, so that everybody does have a chance of getting thrown out eventually. Yes?
Say age-based, is that how long
Sorry.
it took to,
No, I forgot to repeat the last question. Apologies to the streamers. But yes.
When you say age-based, is it how long it took to get to a certain level of fitness? And is the assumption that the lower is the higher is the better?
So the question is age-based related to the number of generations it took to reach that fitness level, and is the assumption that older individuals are more fit. The assumption is that older individuals are more fit because they've survived longer, and your selection criteria is almost certainly fitness-based. So if you have poor fitness, you're going to get thrown out earlier than somebody with higher fitness. But the age-based here is specifically the age of a specific individual. So if you're not throwing out all of the parents every single generation, you could have an individual that survives 40 generations. And the criteria usually is to preserve those older individuals because they've clearly outcompeted 39 other generations. Was there a follow-up or no? All right. And so, yeah, I'm getting close to where we actually look at how this was all implemented. Initialization, it's almost always the best idea to either uniformly generate points across a space, but even better just to randomly generate them with a uniform probability. Because if you already knew good answers, you could locate individuals around that, and start at least a few on a known good answer. But you're really looking for the unknown answers, the other peaks. Maybe the current domain knowledge only represents a local optimum. Explore these other peaks. So you want to start individuals all over the fitness space. Termination, yeah, like I said, if you're doing this, you're almost always dealing with something that has a very, very large fitness space, fitness landscape. It could be many, many dimensions, and so there's an effectively infinite number of potential combinations. You want to finish the simulation at some point. You want to finish the algorithm at some point. And it could be based on number of generations. It could be based, we need just something that has a bit error rate of lower than this particular value to meet our goals here. Or it could be that we've stopped seeing any change. Everybody's converged. And that's actually almost always what it ends up being. No matter what you're doing, you do want the points to converge eventually. And so either you force them not to converge and then you terminate after a certain number of runs, certain number of generations, or you just measure, what's the average amount of fitness change. We were increasing by only 1% fitness per generation. Let's stop the simulation and start a new one, or just see what the results are. So it begins. That's everything you need to set up the algorithm, in general terms anyways. And so you start off this population, you initialize them, you start running, you do the fitness, and you're exploring the space. And some of them will begin exploiting these local optimums. They'll find pieces of a solution that work quite well. They'll begin out-competing their neighbors, and they'll start to converge. I've already talked about premature convergence, so I won't go into that, but they'll converge, and at some point you terminate the condition, look at the outcomes, and say, hey, look, we beat PSK 8, which is what we think we did. And for break signals, who actually wants to go through the really basics of signals? Like it's literally at the level of analog and discrete, or I've gone on already, I can skip straight to the other stuff. Anybody want the signals? Seeing none, onwards.
Maybe do pick whatever you think is the most relevant part of it.
This was really pretty much just thrown in. So yeah, sampling, error is always good fun. These are the slides that I usually show when I'm talking to either a group of amateur radio operators who have never ever dealt with signals other than coming out of a speaker, or a group of people who have just never dealt with signals before. Connect the dots, you know, everyone's favorite challenge. It's that one, right? No, or that one. Aliasing, don't forget Nyquist rate. Yeah, use low-pass filters, they're always good. GNU radio, yes. So I'll show you the GRC plot of our flow graph that we used as the actual simulation. So that's what we used as the fitness function. We ran, I believe it was 100,000 points or 1 million bits through a channel using the constellation that we ended up defining and measured the bit error rate through that transmission. PSK constellations. So this was our problem. You know, this is PSK 8, and we wanted to see whether or not we could improve on this. As you can see, you basically can pick any points inside of the circle. And we didn't feel like throwing darts at a board, and we didn't feel like taking the accepted answer, because what's the fun in that? And to be quite honest, we didn't know any better. So we didn't have enough intuition to be able to outguess this by very much. You know, we kind of got the vague idea that you probably want to spread them out as much as possible from everybody else. But we let a computer make that decision for us. So you can see our constellation just is a mapping between input bits and transmittable symbols. Any questions on constellations? Seeing none. I think that's, yes, this is the end of that bit. So this is the actual presentation. This is where we started for our final presentation. Irvin Tang was my partner for the project. Many thanks to him, as he provided us what are going to be some very nice videos that I hope will play. Project description. RF environments are highly unpredictable and variable, and they can, you know, it's very hard to say what it's going to be through. It's never ever the ideal scenario unless you're in the middle of a RF shielded room. Yeah, the effectiveness of various modulation schemes and various constellation patterns are affected by different parts of the channel. You know, whether you have multipath or whether you don't have multipath, you're going to pick different modulation schemes and stuff like that. So we wanted to kind of generate something that was going to be a general tactic for solving for solution for a given channel. And we're going to evolve them to meet a certain channel. So we modeled this channel in GNU radio. There were some previous works around this, usually with cognitive radios, you know, looking at whether a channel was available and stuff like that. You know, how do you control them? How do you vary power? What frequency do you pick? Stuff like that. But there had never been an actually evolving the modulation scheme. Modulation. Amplitude, you can change the amplitude of a signal. Frequency, you can actually change the frequency of the signal. And phase, you can change the phase at which the sine wave is at. And these are all ways of conveying information. Doubt this is new to anyone in here. PSK constellations, this is exactly what I finished the last presentation with. And algorithms. So these are the three that we actually ended up implementing. Basic evolutionary system. And so you generate mu population, you generate lambda children, and you throw out lambda out of the parent population in all of the children. ES with age layering. So we're going to now divide up the population pool. So if we're going to take the best, say, 10 individuals out of 100 that have survived. We run 10 generations, and we're going to move them into a separate pool, and they're going to compete against themselves. And we're actually going to reset that original pool so that we can explore a different space potentially. All new individuals, all new possibilities. And so we'll see that division in a graph in just a moment. And in this one, you actually have a population of mu, but you're throwing out individuals both from the parents and the children. So the children have a chance to actually not even make it once. And then the island model, which I talked about earlier, where you have actually entirely separate populations that occasionally you spread genetics. You transfer the 3 best from each island to the next island over every 15 generations. This was our experimental setup. And I'm sorry, I'm running Windows, and so I don't have GNU Radio installed, so I can't zoom in on this. We ran without a GUI, so there's really nothing to look at. We'll look at the code in a few minutes, and you can see how this was all linked up with very basic Python. We had a really easy time building our evolutionary algorithms, and then the fitness function is like three lines of code saying, call GNU Radio with this constellation, boom, and returning out the bit error rate. So we had a channel model, and it has a bunch of taps, and we simulated both with multipath and without multipath, and we played with the level of noise and stuff like that as various parameters. I'm embarrassed to say that after a year, I've forgotten what specific settings we set those on and how we played with those and what we ended up using for the final results. But yeah, so we have a random noise source and a file source somewhere. No, we were generating random bits and comparing those after they've gone through the channel model and without going through the channel model. And that was how we got the bit error rate. And that is, but it did work. Again, this was mostly for people who haven't seen radio before. There's an ideal constellation of PSK-8, the standard configuration, and if you add a whole bunch of noise. So just kind of demonstrating the challenges that we were up against to people who haven't looked at radio before. The baseline. So we had a simulated fitness of 1.699, and this is proportional, but obviously not directly related to bit error rate. And that's certainly one of the gaps. Most want to take a look at this again if we were to revisit this and actually have that number be more than just kind of an abstract fitness. It is proportional to bit error rate, but not the straight bit error rate level. For the evolutionary strategy, we had a constellation of Arity 8, which is what we ran everything against. When we went to Arity 16, we ran into this problem. So this is what happens if you generate a constellation with Arity 8, run it through the algorithm. That's one of the best solutions that it found. When you run it with Arity 16, it cheats. Unabashedly, it cheats and decides, no, we're going to run with Arity 8. And so it pairs up points. So you have a 50-50% chance of deciding between those 2 points. But you have a great chance of getting those 2 points localized. So you can improve your bit error rate dramatically by clustering them there. But it is definitely unabashed cheating that I don't think would work very well at all in a real communication system. So actually, great side point. When you're defining your fitness function, you need to take things like this into consideration. And so one of the terms that we should have added in is, if points get too close, that negatively impacts the fitness. So it should have been bit error rate with a little bit of domain knowledge that if you cluster the points too closely together, that's bad. Yes?
The fact that it's pairing like that means that it's necessarily going to have one out of four bits will be wrong every time, right?
Yeah.
Okay.
Yeah. So the implication being that in this, 1 out of 4 bits will be wrong 50% of the time.
Okay, yeah, sorry.
Yeah.
Yes. Well, 50%, if it is wrong 50% of the time, it means it conveys no information all the time.
Yes. Yes.
Did you put a rule of constraining the average power to a certain limit for all the choices it made?
What did we do? When you load it into GNU Radio, the constellation will always be normalized.
Okay.
So the maximum will be constant for the constellation. But you can get points that are obviously located inside of the unit circle, so this will have lower transmitted power. No. Yes. No. Yes. No.
If we're normalizing it,
we're normalizing the max, like we're fitting the cluster of points to a unit circle. So it's simply scaling. It's not pushing all of them to the outside of the circle.
Oh, okay.
And because we're doing both amplitude and phase modulation, you end up with lower power on some of the points, I think. Yes, people are nodding. I'm not crazy.
When you were testing, you said you had a random bit stream.
As the input, yes.
Have you compared to an actual file with audio or compressed data or error-corrected data? Was that something different?
So our input was random, and we didn't test against anything else. That would be an interesting thing to do.
I mean, internally with that, would you expect that to be different? Like you get something with already error-corrected?
Oh, with error correction.
Or the data is, because in real life you would never use white ability.
Well, my recollection is that many systems do attempt to do something to their data to make it look like random bits, because that is a desirable feature. And the thing that I should qualify here is we seeded the random number generator. So the bit streams were all the same for each generation. So we weren't comparing apples to oranges here. Every individual in the same generation was run with the same input stream and same random number or noise source, etc. Yes?
You may be getting to this in a minute, but how are your bits mapped to your symbols, and how is the species, I guess, how is that controlling?
So the question is what was our genotype and how did it match to this phenotype, basically? We just generated polar coordinates, random polar coordinates based off of range-limited integers, or floats, obviously floats. So we generated for arity 8, mapped those rectangular coordinates to polar, and fed that to GNU Radio. Sounds about right. Yes?
So you said you normalized to the max power. Are you assuming an amplifier that is perfectly and equally linear all the way from max power to 0 power?
Yes. Our amplifiers are ideal. Everything in the system is ideal. If you looked at our GNU Radio thing, there's nothing to it. We ran it entirely only in simulation. One of the things that we have desperately desired a year ago was connect 2 USRPs to these, stick them a couple miles apart, and start throwing noise across the channels, because that would be great fun. We never did that. Not actually for lack of hardware, but lack of time. And that, honestly, that and having a room like this review our flow graph are the 2 biggest things that I would change if I were to do this again. And I would enjoy that, especially looking through everything for this talk. It's made me want to sit down again. And we did submit this as a paper, and we got it published as a poster, because at least one of the reviewers very pointedly said, you chose various parameters. Why? And our answer was, it kind of worked, which the academic community does not fully appreciate that strategy. So why did we choose the population we did? Why did we choose the replacement rate we did, the mutation rate, stuff like that? We chose stuff we chose basically rules of thumb. Yes?
Now, I assume you do have some understanding of what would work in the real world also, right? I'm trying to guess why your constellation pattern is very atypical.
Mm-hmm.
And I was wondering whether it's what I think it's Alex implied, is that the low amplitude signals wouldn't do well in the real world. And so from an optimization point, if you had the low amplitude signals, they would probably have gone away because of they were not doing well in the real world, and they would have been pushed out more to the surface. Is that your understanding, or do you not know?
So the question was, how well would this map to the real world, and what parts of it are probably assuming far too much? Kind of paraphrased. I don't know. We did to be at least a reasonable channel model. So we do, there is noise. There's additive white Gaussian noise in the channel. We did experiment with multipath, and we got similar constellations. And we tried a few of the other just drop-in channel models that are available in GNU Radio. And again, we were still getting points in the center like this and stuff like that. So the noise wasn't blowing it out too much. You know, whether our amount of noise was unreasonable, that could certainly be true. You know, we may have been a bit of a channel. Yes?
So your metric was probability of good error at a given power level?
Yes. Yes. I don't know is the honest answer here, but we...
Constellation is normalized, so it's going to be, so that's going to determine the power. So peak
Yeah.
power
Yeah, peak power. Averaged is not, averaged will be varied, peak will be constant across these, and the noise was constant. So I don't know, signal to noise ratio will be variable as well, right? Because you have average power being different, I think. Sure, yeah.
What's the peak power?
I don't know. We could probably, if we ran it again, we could probably derive it, but not off the top of my head. We were using the GNU radio bit error rate block, so bit error rate, which, yeah, which is why something like this would score well, because you could get the wrong symbol, but you would get mostly the right bits, assuming that it mapped the bits to, if it basically went gray coding, I think is the right term, but if 2 out of the 3 bits would match for each of these pairs, then you would get a very good bit error rate compared to a terrible symbol error rate. So that would be a fun thing to play with, actually, and that's actually probably the best way of avoiding this level of cheating. Now, whether or not to think of the problem is up for debate, because bits is really all that matters in the end, right? Various definitions.
Yeah, I mean, the usual design rule for constellation is you want to maximize the minimum distance between constellation points, right?
Yes. Yeah.
And then with the gray code minimizes the number of bit errors for every symbol.
Yeah. Yeah.
So it looks like what you have is pretty close to.
Yeah, and so that's what was matching our intuition. You know, we kind of looked at this and said, well, you know, why wouldn't you, shove those 2 points upwards? That would seem to make sense, but this is what it evolved, and so we're kind of presenting it as it came.
Well,
Yeah.
and that would strike me as just incomplete, running the model longer, or running longer trees would clean that up. Is that right or wrong?
Wrong. We saw convergence. It wasn't going any farther. So let me pull this up. This is...
The biggest difference is when you start varying the noise power level, because probably with the 16, well, it kind of converges to an 8 PSK, it's probably running with a lot of noise, so this looks like a giant fuzz ball. But if you drop the noise power a lot, so it's now like tighter constellation points, it'll probably spread itself out.
Yeah.
Because they'll notice that, oh, now it's these tighter constellation points, so we can actually get a better ER. But this is giant fuzz ball, and it's probably the best thing to do with this.
Not bad. So just before I go to you, so this is one of the plots. This was the best plot that we ended up with, all the presentation slides that we did were averaged across 10 runs. So this is the average fitness across 10 runs, and you can see it very, very, very quickly dropping off and reached 0.64, and that was the best that it got. It converged extremely quickly, which is what you expect from basic evolutionary strategy, because we weren't doing any diversity maintenance. We weren't doing any fancy layering or anything like that. So the next 2 tactics that we looked at have graphs that do converge much less quickly. And we ran everything to 150 generations. And if you just look at this, so these were the parameters. We had a parent pool of 20 individuals. We did 100 mutations upon those 20, 40 recombinations of the 20, and ended up with a child pool of 140, and 120 of those would get thrown out each generation. And I believe that was a fitness proportional survival selection. Yes.
Source code for this thing that you did.
Available on GitHub. Not published anywhere, but I'll make sure it's attached to here. And the
There's a links page. Put it there.
yes, it'll be in the links page, and it should just run. There is a custom bit error rate block that, for the life of me, I can't remember where we improved anything with it, but it is also in the GitHub repository. Yes.
What is the CPU time at a single 150 generation run consumes?
What were we seeing?
I'll take roll calls.
It was on the order of 15 minutes, 20 minutes of wall clock time. I'm remembering tens of minutes, not hours. We had scripts running these on multiple servers, and that's without any GPU acceleration or modern processors. So if you were running this on a machine dedicated to signal processing, I'm sure you would be just absolutely flogging that time. Yeah, we did many runs, so it wasn't that long. Questions? Yep. If anyone's getting bored, feel free to start, chucking pieces of paper at me. Hey, there we go. It's a movie. It plays. Wonderful. And I think it will loop around. So you saw the convergence there, and it converged extremely quickly, and ended up with this very appropriately chromosomal resembling cluster. And again, I'm kind of a non-intuitive result for us, probably indicative of low noise, as you were saying, or high noise rather. So if I boot that, yes. So you can see extremely diverse, converges quickly, and then so the red points are the best fitness individual for each generation, and the blue are all of the other points of the other 20 parent individuals. Sorry?
I mean, I'm trying to envision why it's doing that. And it's not the level of noise, it's the color of the noise. The noise is color.
We were using white noise, I think. So.
You said the signal might be
Not in these runs.
Oh, okay.
All these runs were done without multipath. The multipath was kind of an experiment to see whether we'd get dramatically different results, and the answer was no. So this is the age-layered population system. And so Arity 8 again, 150 generations. You'll see one of the points why we got a poster, not a paper. We have 143 children produced because of the 3 elites. And so we were running more simulations in this because we had 3 additional individuals per generation. Strike. But very order of magnitude of simulations. And so this graph obviously much more interesting. And what we have here is, so this is the first pool. And so this is up to, I believe it was 5 generations. So you'd run five generations, pick out the best few to an entirely separate pool, and initialize the pool with those individuals. And so you'd see, this would kind of dominate a band of fitness. And so another 5 generations down, they would get transferred to the next layer. And the reason why these are discontinuous is because there is a mutation and recombination step in between them. And we're plotting the best individual here. Because we were taking only like 5 individuals from the top pool and had to generate 20 parents out of that. And so that's why this is discontinuous. But you can see pool 1, pool 2, pool 3, and then pool 4, 5, 6 ended up quite close to each other. But you do see it achieves a better score by 0.03. Again, what that exactly means, don't know. But lower bit error rate is actually what it means, but I don't know by how much. And so that's a problem with our model. But this was a very cool and clear graph, so we particularly enjoyed how that ended up resulting. Best fitness, mean fitness. Very similar graphs. You can see that it doesn't achieve quite as low of a point, but it's quite close. And here's a model. Here's a video of it. So going clockwise, you can see the tiers of population. And particularly down here, well, and up here, you can see when new genetic material is introduced. And so the lowest pool would evolve, potentially a completely different approach, or at least a different set of individuals. And I don't know why they ended different lengths. They were all run for the same number of generations, except for at the very beginning, obviously, because some of the generations had no individuals to start off with. But yes, scrolling anytime now. Yeah. And the final diversity maintenance tactic that we did was the island model. So we had 4 islands, 4 pools of population, 15 individuals per island, generating 105 individuals per island per generation. And this was calculated out to be a similar order of total fitness evaluations, which we thought was the best metric for comparing between the algorithms. Shame on me, I don't mention how often individuals were moved between islands, but I believe it was on the order of 10 generations. The best 3 would get moved to the next island. And so you can see the slope of all 4 islands was very similar. And this graph doesn't show it nearly as well as some do, but you can see at various points there's sharper drops, not so much down here, but there's some points where when individuals are moved between islands, there would be a very rapid improvement in fitness. And this beat the basic PSK8 and ES, but didn't beat ALPS. ALPS was the best tactic at the end. Best fitness, mean fitness. So the interesting thing is that this one island was so far ahead of the others, and so that's almost certainly where the best individual evolved right at the beginning, and then took over that island pretty much, and then continued dominance of that island throughout the entire simulation. And again, you can see the videos of the points converging. What's interesting is that they don't converge nearly as much, and I believe that's because of the more frequent introduction of new genetic material than in the other models.
Is it surprising that the 4 islands, that there was one island that was so far ahead of the others if you were transferring the fittest individuals?
I would have expected all of them to converge at the end. I would have expected one of them to be out ahead early on, and then as that individual got moved around. But either that's indicative that we didn't move enough individuals around, and so despite having a very strong fitness, they still died off. They were overwhelmed by the native populations of the islands. That's my best guess, which probably means that we were running with poor values for either fitness selection or survivor selection or parent selection, or we should have just moved more. And I think that's pretty much the end of this. Yeah, conclusions and future work. At least in this simulation, our constellations were beating standard PSK8, and that makes us all very suspicious, or makes Irvin and I very suspicious. So we're pretty sure that there are lots of holes to poke in this, but we have yet, this is the best round of input that we've had in terms of hole poking, so much appreciated, thank you. Yeah, there's a whole bunch of other techniques that we didn't do. We gathered reasonable statistics that weren't shown here, but we'd like to do more. And real world testing, you just can't beat actually transmitting something, because then you don't need to know anything about the model. But yes, we'd love to do that. And that's the end of all the slides. I can go through code, but we are getting on in time, and there is another presentation, so I should probably get off the stage at this point. I will make sure that everything gets posted up, and you guys can browse through it, and my email address will be there, and I would love to talk about this. But I will go through questions. So, yes?
What sort of bit error rates were you seeing in the translation?
Well, that's where I can't actually say, because I don't trust our bit error rate measurement, which is what this fitness function is supposed to be, because we were getting a value of 1.6, which is just bogus. So there's something very wrong with what we were doing there. We were seeing it improve as you put more and more reasonable constellations in, but yeah, so we don't know. But it would be very, very easy to share our best fitness constellations. So if anyone would like to try this out, I'll make sure to list like our most fit individuals, and you can run it through and see on a model that you trust and bit error rate that you trust. And I'd love to. That's basically where we need to improve this, because things got better, but we can't measure it, which is poor science. Yes? Well, thank you. Hope that was it.
Thank you very much, Derek. So let's change over, and then we can get into Alex's presentation.
You did say over an hour, right? Mac.
Yeah. Well, does anybody have a does anybody have a
Thank you. We had a lot of fun with the project, and there's certainly a lot more to do with it, but and there is a deep level of suspicion when you start beating something like PSK8, because you just know somebody's sat down.
One thing I was wondering is, as your energy level decreases due to noise, and so your constellation squeezes, I'm wondering, the 2 points here will be equidistant, but they'll squeeze towards, so I'm wondering if these guys will squeeze together like this, or do they stay equidistant as you get closer to the, and therefore the distance between the inside points gets smaller, but the distance between the inside and the outside points stays the same.
Sorry, why would they be converging towards the center? I would because if you were increasing noise,
as long as you don't normalize, but you keep the same power level, which is a very typical thing,
right?
It'd pull in that the inside points would end up being closer together,
right?
Because they have lower power.
There are alternate 8 PSK constellations being used now.
Okay. Yeah, I'd love to see that. Because I'm foggy enough that I didn't want to say this in front of the entire room, but my recollection is that PSK8, like PSK4, there is a known, proven, optimal, solution. But for PSK8, I feel like there isn't, actually. And I can't remember whether that was that 8 or 16. And of course, the other thing that this is doing is it is optimizing for the very specific channel. And so if you ran this through, it's quite possible that PSK8 standard, unit circle is the best average performing.
Yeah, there's a new satellite standard called GBB S2 extended.
Mm-hmm.
They've got a zillion wacky constellations. You're gonna love it.
I would definitely love to see that.
So, you said earlier that you showed this sort of butterfly-shaped 8.
Yeah.
But the stuff you showed later in your presentation was all, it seemed to have 8 points that were ambiguous to 4, as if they were 4. So
So the ones that I showed where I said it's cheating, that was.
You showed the 16 that was cheating. And
right.
It looked like the 8. It looked like the 8, but then you were talking about, you were saying all of your main.
Oh.
You had 8s that were cheating by being 4s.
Yes, and this is where part of it being a year ago comes into play. I can't remember whether the one that I showed that was wider spaced out was like a different channel model, or with multipath, or with less noise, or something like that. So the only thing I can guarantee is that the PSK8 standard and the three that were in the final presentation, all of those were done under the same channel model, noise, and stuff like that. But I don't know is the real answer. Yeah. Oh.
For trivial reasons.
Well, we should be able to run most of it. There are several copies of the source code at this point, and so determining which one actually mapped to which result is a little difficult because it wasn't all stored under Git. At various points, it was copied out and shared as zip files and stuff. And there was certainly because it was a class, we continued to implement it again and again and again until the yes, that's a good point.
Scintillating and interesting because it's been streamed to a worldwide audience.
Oh, I think so.
Immortalized forever, yes, that's right. Nothing compromising, I hope. So, whoever wants to don this first.
Alright, I guess I will.
It's fancy.
Yep. Aye.
Ah, okay. I have the talisman. Yeah, but I can. Next time we give a talk here, you could do that. If we give a talk here again, you should do the next one.
Okay, that works. I can do that.
On the VCO, or the VNA. I feel like this thing is saying.
So we might get underway again with our second. We might get underway again. Thank you. We've got our third presentation now. I'm going to hand it over to Alex Ray. Take it away.
All right, thanks. I know it's kind of getting late. Learned a lot so far today. I'm so glad I got to come out. This is my first time here. And so I'll keep this really short. And I'm Alex. I'm on a team called Team Lunarnaut, and we're entering in the recently begun NASA Centennial Challenge called the Cube Quest Challenge. And I'll talk a little bit more about it in a second, but essentially we're going to send tiny radios into space, or that's the goal. So here's the NASA splash for the Cube Quest Challenge. It's sending 3 U CubeSats, which there's tiny little diagrams of there. They're satellites about a little smaller than a shoebox, 30 centimeters by 20 centimeters by 10. Your entire satellite has to fit in there. This includes any sensors, experiments, imagers, navigation aids, and radios and antennas. It was proposed late last year by the Centennial Challenges Committee, and it got funding. So it began early this year. And the challenge is to send a small satellite to either lunar orbit or deep space. And deep space is defined as 10 times the Earth-Moon distance. The nice thing is you don't have to pre-declare this, so if you happen to go and miss the moon, you can always enter in the deep. And the nice thing about this, especially as it relates to this meetup in particular, is it's essentially a radio competition. It's a bandwidth competition with 2 separate parts. One is a burst mode, which is how much data can you get from your satellite in 30 minutes. So you can assume, it's right overhead. You can try this many days until you get a day with good, clear conditions. You can go out to an area with low noise. And the second data rate competition is over 28 days. For the lunar competition, this is almost a whole lunar cycle. So how much data can you continuously get over 28 days, potentially utilizing multiple ground stations? You're not limited on your ground station usage. You're not limited on what lunar orbit you get into, whether it's Earth synchronous or polar, or something that would allow you to see the satellite more of the day than you would be able to otherwise. And the last really important thing is that it does have cash prizes. The cash prizes are probably going to be small compared to the cost to develop this technology, but they're not insignificant. This is the largest Centennial Challenge NASA has ever funded, and it's got a total set of prize barrels, I think, at $5 million US. That link will get you more info on it. So we started a team, and we started building some antennas, which I have up here. Mostly out of stuff we found at hardware stores. And this is where our first interesting application of software-defined radios is. We happen to have somebody, Michael, who had a tracking generator, signal analyzer, and directional coupler. So we were able to do some really, really nice tuning and match analysis on our antennas. But that's not always the case for other teams, and even that setup's got limits. A big factor in this competition is probably going to be the ability to make custom antennas. Like we just saw, evolutionary algorithms are probably a really, really good way to design great antennas. But a big value to us is not necessarily how well does it do in design, but how fast can you tune them. So sort of a rapid iteration approach. What we showed, and what I have here I can grab in a second, are starting with UHF and VHF antennas that are specially tuned to satellite frequencies. So as ground station operators, we can start by listening to existing satellites, amateur satellites, as well as research satellites that we can sort of find and figure out what their telemetry streams are. The signal generator, tracking generator, and signal analyzer allow us to tune in very precisely to the bands we want. But we'd like to move this up to a software-defined radio. This is actually, I think, why I'm speaking here today. Is I asked Ballant on the Meetup group about talking to people about using an Edis Research software radio, the 2x2 with directional couplers as a vector network analyzer, and so to be able to analyze our radios, amplifiers, and antennas that we'd use for the competition. This is something we'd like to do more of. It looks like it hasn't been implemented yet, but it is on the GNU Radio Google Summer of Code list of projects, which is awesome and exciting that might get done this year. And there's lots of other designs possible for antennas, and as a bonus, here's our 2.4 gigahertz lightsaber. So up here, I'm going to grab these real fast for the live stream. These are both our beginner SATCOM antennas. This is UHF, and it's a design by WA5JVD. It costs about $10 in hardware store components. The equipment used to tune it probably cost a lot more than that, but again, this is where software-defined radios are really great for. And it's tuned to a 1 megahertz wide band matched around 435 megahertz. And this is another one. This costs, I think, also around $10 in hardware store parts. And this is VHF. And it's a model by WB2HOL. And it's almost right on the nose, 145, I believe. Right. So also, what's really interesting. I feel like they're swords at this point. I'm going to hurt myself.
One more with the proper camera going. Yep, strike a pose, that's it.
I think this is the best I'm going to be able to pose. So what's really interesting is those phrases underneath are in fact the web searches. The first thing that comes up for the search of a cheap Yagi is the UHF antenna, and the first thing that comes up when you search for a tape measure antenna is that the model for the VHF. And like this 2.4, we'll be making our own antennas as things go on.
Now you did some tuning on those, right?
Yes.
And are you tuning the links to the elements, or what were you doing?
All of the above. You want to come up here and answer that, Michael?
So on the UHF antenna, we changed the feed point left and right to change the point where we have ground tied to this dipole half, and then we're also changing the length of this loop, since this isn't just a dipole. And this loop helps with the coupling, so you don't need a matching network, and it comes in very nicely close to 50 ohms. So we changed the feed point mostly, and a little bit of length change here. On our 2-meter guy, the lengths in the example were spot on to begin with. Measurements made out of tape measures helped too, I guess. We kind of counted it out in 1/16 of an inch. And
Still gotta know where to measure from.
very true. And then this guy needs a little hairpin match to help him along, and with the prescribed hairpin match on the same website, right at 50 ohms, so or close enough that my elderly meter can't tell the difference. So, yeah. Mm-hmm.
Yeah. So this helps you with the this matching, but there's no particular clever trick within the SDR or anything that helps you make sure that the rest of your parasitic elements are give you a good gain, right?
Correct. So what you want there is a reference antenna and an antenna range, and so then you need a full duplex SDR and
The matching.
yeah, all sorts of other fun stuff.
So after the antennas, let's see if I can get this thing to go away. The next thing we expect the radio design is going to affect in the competition is the choice of protocols and modulations. I really love that I went right after a modulation design and ways of picking that, because that will probably come into play here. Most of the deep space network are, it's infrastructure built to talk to things that are much older than modern modulation techniques, modern radios, modern amplifier construction techniques. Things like turbo codes didn't exist when these things were launched, so they're not really often considered. We're interested in using SDRs on the ground because it allows us to sort of deploy ground stations, as well as sort of do far range tests, balloon launch tests, and things like low Earth orbit demonstrator satellite missions with an adaptable radio that we can just sort of try one thing, try another thing, try another thing, and see what works. Even for a competition satellite, it's possible that you could go to the moon without knowing what your protocol is. You spend a few months sort of measuring and designing, and then for one particularly good day, you pick a given protocol and you try that for 30 minutes, and that's the burst competition. So that's something we're hopefully going to be able to do. Here's our initial tests. I'm still very new at GNU Radio, so this was my just clock phase recovery and recovery on a noise in a QPSK. Where we're still, I'm still very new at this stuff. I'm still very new at SDR, so I'm glad I got to come out here. I'm glad I got to learn a lot. But we did try one novel algorithm, which is the picture I sent to Ballant at the before this talk, which is something I jokingly called Batquam. And it's just a set of constellation points that maps out the Batman symbol. It turns out it's a neat hello world for our ability to create our own constellations as we're sort of building and testing our own radios. And we made it for sort of a proof of concept to make our own SDR. Instead of using an off-the-shelf one, the SDR that goes into the satellite will probably have to be homemade, so we might as well get good at making them now. The source code's up there, and it looks like that. So yeah, it's 64 points. I think we pulled it off a vector image that was just pulled off the internet. Ended up working out all right. So this factors in, and this was an experiment along the lines of radio design. So the third big area I think the SDRs will come into play in this competition is the ability to design, custom build a radio that do very well on the satellite side. Ground station has a lot of opportunity to do really creative things like supplying a lot of power, potentially getting a synthetic aperture, getting a lot of aperture, doing things like liquid cooling the amplifiers. You really can't do that in space. So the design of the SDR, while you want it to be flexible to modulation, has to be pretty optimal in terms of consumption and then ability to transmit in whatever licensed spectrum you're able to get. The history in this, the small sat field is mostly low Earth orbit. Low Earth orbit satellites have different radios than they do for deep space. And the radios we do have for deep space don't fit on small satellites. So you're almost certainly going to have to design your own radio to enter in this competition. And another interesting point for the radio design is again the power consumption. I actually think after seeing Derek's talk that it would be very interesting to build a GNU radio model of transmit power consumption by the amplifier and see how evolving a modulation scheme that uses less power wasted by the amplifier does.
What are typical differences between the radios on the lower Earth orbit and deep space radios?
One is the ability. What? Oh, the question was, what's the difference between low Earth orbit radios and deep space network radios? Certainly, all of these. I'm not an expert in space radios yet, but some examples that come to mind are you have different free space loss considerations. Low Earth orbit is still close enough that lower frequencies like UHF and VHF do very reasonably, where your free space loss over at sort of the moon or deep space at those frequencies is almost untenable, at least for this size antenna aperture. Another thing is that these radios are often used for beaconing as well. So not only are you communicating with it, but you're using phased arrays on the ground to figure out where your satellite is and using to its navigation operations. And I'm not sure what else. I think power utilization is another big thing, as well as directionality becomes much more of a something in question. In low Earth orbit, you have Earth's magnetic field, which you can both use to point as well as sort of control attitude, and you're able to do neither of those in deep space. But that is a great question. I should learn more about that, but that's all I have right now. A question about the competition, is it bidirectional or one-way communication? It's one way. It's how much data can you get from the satellite to the ground. And in this way, radio setups are often very asymmetric. Very low data rate links up, mostly for command and control. And data links down are often very high bandwidth, either imaging, results from whatever science or sensors you have on board, things like that. So much more downlink than there is uplink. Now there is an exception to the rules I just gave for why small sats usually don't have these radios, and that is the IRIS/Inspire project from JPL, which was making a deep space network compatible radio for CubeSats. So they were trying to launch very, very, very far away and still be able to track them using the same deep space equipment. So here is one of the designs for the Inspire satellite. It's very small. This is, so if you imagine that main body being a square tower, it's about 10 centimeters by 10 centimeters by 30 centimeters. They're using a custom designed X-band radio that, right here, which is essentially a miniaturization of the existing deep space network X-band radios. The competition has stated that this design, even though it's never been launched, is considered outdated, and they want the competition entrants to far outclass it in terms of power efficiency and data rate. But it makes a good starting point, as well as it's compatible with the Deep Space Network, which is an array of antenna dishes around the Earth that you can kind of rent time on, and you'd be able to rent hours of aperture that you could use to talk to your satellite. So here is our crappy little first pass radio. I know many of y'all, this is old hat, but for some folks, even if you end up using software-defined radios a lot, maybe you haven't had a chance to make one yet. So in exploring making a radio for the satellite, we started out with the basics. On the left is just a voltage-controlled oscillator tied to a power supply, and we just twiddled it until we found it in this waterfall plot that we were looking at with a software-defined radio. And this is just, so from the output of that, we have a splitter, 2 cables that are hopefully about a quarter wave apart, mixers and a combiner, and we are able to sort of twiddle that with a microcontroller as the baseband, which is the same microcontroller that was doing the back QAM earlier. So this is kind of, again, this is our learning experiment is first making a radio, and then it's going to be miniaturizing it, it's going to be power optimizing it, and then maybe sending it to space. And we have some initial results, which I'll go through very quickly. It's the first time we were able to catch what was basically, I guess, BPSK, which is we're only modulating one of the just, I think, I instead of INQ. And there's more data on that that we were able to catch. And I think that's it. Yeah. Questions? You can kind of see this is the little carrier moving, I guess, not carrier. Yeah, that's FSK, that one. Sorry.
Related to the power requirements, are you familiar with the work by Chris Testa on HC of the Future?
No.
Okay. What he's doing is really low power software-defined radio that you can put in a handheld device using low powered FPGA.
Okay, so it's Chris Testa. I'm trying to repeat this.
White box.
White box. Apparently has a really good. It has a really good, I guess, demo of low power software-defined radio using low power FPGAs.
Yeah.
Get that right? Cool.
They're flash-based instead of SRAM-based FPGAs.
Okay, repeating that, flash-based FPGAs instead of SRAM-based FPGAs. I'm going to check that out. Maybe live stream watching people should check that out too.
We have a question. Is solar the only power source?
So this is actually something I do know a little bit about. So satellites are really tricky in what you can and can't put on them. Nominally, the CubeSat is just constrained by the size and weight. But because you're a small sat, you're often launching as a secondary payload on somebody else's primary payload launch. And so there's huge, hundreds and hundreds of pages of rules about what you can't do to endanger the primary payload. These often include no pressurized vessels. So if you have electric propulsion, all of your fuel storage must be solid state. You can get write-offs on things like that. But if, for example, as an alternative power source, you're going to use an RTG, you'd have to get that approved by the primary payload. They would have to, you'd probably have to go through an experimental campaign, partly self-mandated, partly mandated by them, to prove that your radioactive power source is not going to endanger the primary payload. Nominally, the launch is the launch of this competition satellites, the winners, top 3, will get a ride on SLS Exploratory Mission 1. The location of the small sats in the SLS is, I believe, like 16 inches above one of the cryogenic hydrogen tanks. So they're going to be super insistent that that thing not do anything to endanger the hydrogen tanks, and therefore the whole SLS mission. But within that, alternative power sources could be managed. It's definitely not a requirement in the competition, though because of past CubeSat research and payload limitations of the SLS EM1 mission, most competition entrants are going to be expected to use solar, at least for a large part of their power.
So about that,
were 3x stabilized, it would have a higher power generation. How would you spin stabilize a CubeSat? Like, does it have some thrusters here and there?
So the question is kind of how do you spin stabilize a CubeSat? I think especially in the context of outside of Earth's magnetic field, where you can sort of torque based on your magnetic fields. It turns out there's a lot of really interesting answers to that. One of the just an example of that, the one that my team's been looking into, is what's known as ablative thrusters. And so that big structure in the satellite, most of its strength and durability is to survive the forces that you undergo in launch. It's a lot of shaking, it's a lot of jittering. After that, in space, the forces on the satellite, the structure itself are very, very small. So you can actually use it for thrust. You just put a small arc plasma across it and ablate it and just spray some of that structure material off one corner or one side or the top or the bottom. You can torque yourself and point. But there's lots of options for it. Most of them involve spraying matter in some way or another. So if anybody else is curious, we're not the only team in the Bay Area. A bunch of teams in the Bay Area. They're definitely going to be looking for people with expertise in software-defined radios. Like I said, most of the teams are probably going to be not only looking at making their own antennas, but making new kinds of antennas, making new kinds of protocols, and making new kinds of radios. So there's a lot of cool stuff to be done for it.
The satellite is that big structure you showed there.
Yeah. So when I showed the Iris / the Inspire satellite, I think it's called, that the satellite is the whole structure.
And so it looks like there's things that deploy once it's separated, right? Solar panels. And you also could, by implication, deploy antennas on that also?
The question is are we allowed to deploy antennas? And the answer is definitely yes. In fact, I believe it's expected that everyone will be deploying antennas in some kind or another. The NRO, who is an American organization that launches a lot of very advanced satellites that we can't know about, has, I believe, they have contractors that deployable sort of umbrella-like meshes to use as reflectors, and they work well up into the gigahertz range, potentially meshes that are 12 feet to even 30 feet across. Deployable antennas work that way. MIT did an experiment where they had a metallized plastic film that they sprayed some powder in and inflated like a balloon, and they used that. So they had a little arm that was at the focal point of this inflatable parabola and tried to use that as an antenna. There's lots and lots of ways you can deploy antennas, and so that's probably going to be a big part of this competition.
And you're focusing on 2 meter and 70 centimeter just because of the ground station pervasiveness of those things.
Yeah, we're focusing on the UHF and VHF, the 70 centimeter and 2 meter right now, because it's easy to make the antennas for. It's easy to get radios that can process it. We can sort of not transmit as much, but we can receive the digital telemetry from a bunch of existing satellites and sort of learn and iterate on that before going into sort of the higher frequency bands. It'd be harder to make a 7 gigahertz version of one of those.
What's sort of the timeline on the development here?
Question was about the timeline. The competition, the NASA competition has 4 ground-based tournaments, starting in August this year, every 6 months. And I believe the last one is then in February 17. Yeah. And so they give feedback during each one, but the score in the last one is what really counts. The top 3 teams in the the last ground tournament are the top 3 teams that NASA thinks have the best chance of flying the mission successfully. Those 3 teams will get a free ride on the SLS Exploratory Mission 1. They'll get slots in the satellite deployer. And they'll deliver to integration, which means they put their satellite in a box and ship it to NASA, or hand it off to NASA in March of that year. And I believe right now the launch is not scheduled till September of 2018. So it will sit in the integration bay for a year and a half. These things are launched entirely uncharged and off. So often there is, and this might be the case on this mission, where a month before launch, they will optionally charge up your largest array of batteries and then power you off again, so that after launch and deployment and all that, you have a little bit of energy to go off of before you have to start gathering energy from solar or whatever your power source is.
Do they provide any testing facilities, environmental testing facilities, or anything so you can make sure that your gears don't work in climate?
So the question is about do they provide any environmental testing facilities for to test and see if your equipment will work? The answer is nothing specific for this competition, though NASA does provide these services, and the various NASA research centers like Dryden and Ames and Marshall do provide these services. There's no special provisions for this competition that allow us to get them at a free or reduced rate, except for one. The one service we get as for free is deep space network ranging. So NASA will give you 8 or 9 hours of time on the deep space network antenna dish in the US to talk and point and beacon at your satellite to try to figure out if it is in fact in lunar orbit or not, or if you're in the deep space competition, if it is at the 10 times Earth-Moon distance or not. And that's just for the purposes of their own validation as well as yours. Did you get there?
Wondering about radiation hardening.
So the question is about radiation hardening. There's a lot of really interesting theories in the industry about what to do about radiation and potentially bit flip errors, single upset errors, things like that. Some of the components that make up software-defined radios, if they have very, very small transistors and large arrays that you use to do a lot of math, will be particularly vulnerable to this. There's some mitigating techniques, like silicon on insulator and ferroelectric RAM, that are going to be a little more tolerant, that are fairly new. So we're just starting to see chips made with these. If you have lots of money, like oodles of money, you could take whatever chips you want to use in your radio, in your satellite bus, and you can take them to a company that will radiation harden them. They'll basically pot them in shielded, like well-known controlled, and test that it is shielded and things like that, but that's very expensive. And the other thing is you have a large distributed system in your bus, such that you have a lot of processors, you have a lot of FPGAs, things like that, and they're always reflashing each other and verifying each other. So you hope that even in the event of bit flips and upsets, that it would recover and recover quickly. But yeah, it's the subject of a lot of really interesting research. I don't think there's one approach that I know of right now that'll do well in this competition. Another question. The question is about the rocket we get a ride on. So the top 3 winners of the 4th ground tournament get a ride on SLS Exploratory Mission 1. Or at least that's the plan right now. Other competitors that aren't in the top 3 can pay for their own launch, and that might be a low Earth orbit launch, because that's where most of them are these days. But the SLS Exploratory 1 mission is actually, right now it's planned to sort of loop around the moon, and kind of like this big figure 8. It's a bit more complex than that. We'll go out past there, and the primary payload is going to be going through that point. So the little part of the rocket that the secondary payload is attached to will also be going through that point. And part of your parameters is figuring out where you're going to get dropped off in the part that's looped around the moon.
Yeah, I asked the question about how would you get to the moon if you don't have a propulsion system, but we're taking you there.
Yeah, so one of the questions is how do you get to the moon with regards to the propulsion system? That's a big unsolved problem right now. It's hard for a very, very small satellite to thrust all the way from the Earth to the moon, especially in a year's time or less. If you have 5 years, it's a bit easier. It's not something I have a good answer. If a team was to get a ride on the SLS Exploratory Mission 1, they'd get a lot closer to the moon than you would otherwise. The question is, are we looking for sponsors? I feel like the answer should be yes. Actually, I hadn't thought about that yet. A lot of teams probably will be. There's teams operating out of universities especially are going to be probably short on funds and also looking for in-kind donations. So anybody that makes potentially antennas, radio equipment, batteries, solar panels. Going to be honest that I kind of started this team and I'm working with this team, and we're all in this because we're curious about it and we want to learn more about it. So, our solution to needing antennas is building antennas. Our solution to needing radios is building radios. Yeah, self-sponsored right now. How far do I think we can get with that? Probably not top 3 of the 4th ground tournament, and probably not even being able to deliver a satellite to NASA integration. Realistically, entering in the first 2 ground tournaments. So the first basically being a mission presentation, create a mission that would, in theory, succeed. Second being that plus a lot of experiments and data backing it up. And then just build a low Earth orbit satellite instead and see if can go around begging for launch space on a bigger launch via the CubeSat Launch Initiative or things like that. That would allow us to basically build our experimental radio system and find somebody to put it into low Earth orbit space and be able to do the experiments we want up there. All right, thanks so much for all the great questions.
Thank you very much, Alex. I think it's undeniable space is cool. So good luck to you and your team. All right, well, that brings us to the end of our 3rd Cyberspectrum meetup. I think we're all done, but if anybody has any announcements or ideas or anything, now's the time to speak, or hold your peace until next month. But thank you very much for coming, and keep an eye on the webpage. We'll try and post all the materials. And thank you to our presenters once again, and see you next month. Good night.
What's that?